last chapter, we learned how to do electron dot diagrams, and we learned about covalent and ionic bonding. This chapter, we're going to focus upon growing out our skill with the electron dot diagrams, and those are two-dimensional representations, and they do not have regard for the three-dimensional geometry. In this chapter, we're going to work out the three-dimensional geometry, and we're going to learn about two competing bonding theories. One bonding theory is going to be called MO, or molecular orbital theory, and the other bonding theory is going to be called VB, or valence bond theory. Theories explain things we observe and predict things we have yet to observe. But things we observe provide evidence for the theories. And for one, we observe certain shapes. Some molecules are linear, like carbon dioxide. Other molecules are bent, like water. Other molecules are planar. They all exist in one plane, like boron trihydride. Other molecules are pyramidal, trigonal pyramidal, like ammonia. And then there are T-shaped molecules, like I can't tell what that one is. And there are other shapes. There's a good number of shapes, and I'm going to be handing out to you a very good summary sheet of this shape issue with all the possible shapes and the situations that cause each shape. When you get that sheet, it's going to be imperative that you memorize all of it. This is an important table that will allow you to determine the shape of any molecule that you're capable of determining the electron dot diagram for that molecule. And so we're going to learn what it meant by what counts as an electron cloud, and the parent structure, and then the actual molecular shape. And we'll learn about this, and then I will bring up this slide later in this presentation. A Lewis structure gives atomic connectivity. This tells us which atoms are physically connected to which other atoms. The shapes of the molecule are determined by bond angles. This molecule, HNH, has a bond angle of 107. Not all molecules are planar. When you draw this ammonia on your paper, you probably draw it on a flat piece of paper, like flat Stanley, and it's two-dimensional. But if the electrons get as far apart from each other as they possibly could, because they all repel each other, you can predict the shape. We call this model the valence shell electron pair repulsion theory, VSEPR. VSEPR. This will be very important for understanding properties like viscosity in Chapter 11, and will also be important for understanding Chapters 25 when we learn about structural isomers. I know your book discusses this thing called electron domains. I like to call them electron clouds. Lone pairs count as one electron clouds. Single bonds count as one electron clouds. Double bonds count as one electron cloud. And triple bonds count as one electron cloud. So never mind the B molecules you see here, but the A molecule in the middle has 4 electron clouds around it. It has 2 from the single bonds, the double bond count as 1, and the lone pair counts as 1. So it has 4 electron clouds. So its electron domain geometry will be based upon 4. VSEPR theory suggests that the best arrangement is one that minimizes repulsion amongst the electron clouds. So when you have 4 electron clouds around a central atom, the best way to make everything as far apart as possible is to form a structure which we might call a tetrahedron. You would think that if you had a 3-sided pyramid, that would be a tetrahedron with one at the top, one left, one right, and one over there. And the predicted bond angle of a tetrahedron works out to be 109.5 degrees. Who knew? If you have 2 electron clouds around a central atom, they get as far away from as possible if they form a 180 degree angle. When you want to keep 2 people away from each other, you stick your hands out in between them and you try to get them out as far away from each other as possible. If you would put your hands above your head close to each other, they would repel until they would go further away. If you would overdo it and put your both hands down by your sides, then they would be closer together and they would repel. Your 2 hands repel as best as possible if they are at a 180 degree angle. If you have 3 things that you want to stay as far apart from each other as possible, then you would get still a planar structure, but it would be a 120 degree angle, all on one plane. We call that structure trigonal planar. 4 things as far away from each other as possible, you get a tetrahedron. Now, when we've represented 4 things, like in the molecule CH4, methane, or in carbon tetrachloride CCl4, we have represented these molecules as having 90 degree angles, but that's simply not observed. So they're not 90 degree angles. That's not what we see. There are 109.5 degree angles when you have 4 things around a central atom. 5 things, you get a double pyramid. The term that our books like to use is trigonal bipyramidal. Notice in this diagram here, the molecule has 3 around the middle, and then 1 up, 1 down. If you would connect all those faces, you'd have an upper pyramid and a lower pyramid. And the structure you get with 6 electron clouds around a central atom is called octahedral. Now, that's just ridiculous, right? Isn't octa mean 8? So what's this use of the word octa when you have 6, when octa is for 8? That's clearly a source of confusion. Well, when you have 6 clouds, if you were to connect all the dots and build faces, and this is what the Candy Lab is all about, you have to be able to visualize it and build it in some sort of a modeling setting in order to understand this. If you have 6 things, if you connect all the faces, you get 8 faces. So that's why the structure is called octahedral. And all the faces are related by 90 degree angles. Now, I've presented a lot of information here, so feel free to stop the podcast, go back, listen to something. If you don't understand what I was saying, write down your question, email me the question, be prepared to ask about it in class. These are electron domain geometries. Okay, now we really haven't talked about shapes yet, so these are the parent structures. It's so simple to get the electron domain geometry, or the parent geometry. All you have to do is count the number of electron clouds in the Lewis dot diagram we learned to do last chapter, and that'll give you the electron domain geometry. But you don't have the molecular geometry until you differentiate between bonding pairs or non-bonding or lone pairs of electrons. In this ammonia molecule, there are 3 bonding pairs of electrons and 1 lone pair on top of the nitrogen. So in the structure you get here, the top part of the pyramid is missing because the hydrogen that would be up top isn't there because there's an empty space there. There's a bonding pair there. So you don't end up getting a tetrahedron. What do you get? So if you had the last hydrogen in ammonia there, you'd get a tetrahedron, but that top part is missing. So when you subtract out the top part of a tetrahedron, what you're left with is like a tripod or trigonal pyramidal. It is acceptable to call that shape either tripod or trigonal pyramidal, but it is not acceptable to call it trigonal planar. See, because if you look at the last structure on the right where the nitrogen is, where the blue nitrogen is, above the nitrogen is the lone pair. And that lone pair has 2 electrons closely held to the nitrogen, and it has repulsion. And it pushes the 3 hydrogens downwards a little bit to minimize the repulsion because of Coulomb's law, which I know you're learning about in honors physics this week. Or not, if I play this podcast again next year. The molecules water, H2O, ammonia, NH3, and methane, CH4, all have molecular domain geometries of tetrahedral. But water, represented on the bottom, has 2 lone pairs, ammonia has 1 lone pair, and methane has no lone pairs. So the water molecule ends up being bent, even though it's that same 109.5 degree angle. Ammonia is trigonal pyramidal, and with that same 109.5 degree angle, and methane or carbon tetrachloride would just be the full tetrahedral. If you take a tetrahedron and remove 2 hydrogens, then you get trigonal pyramidal, or bent, well, I guess you get the bent if you remove 2, or trigonal pyramidal if you remove 1. It turns out that the angles aren't exactly 109.5 in ammonia and water. And hopefully you didn't just memorize that 109.5 when I said it earlier in the slide, but there is some change in it. Let's chat about that. So your classic linear molecule is carbon dioxide. And the Lewis dot diagram for carbon dioxide is on the right. Even though it's got 8 electrons around the carbon, 4 bonds, or 2 double bonds, that counts as 2 electron clouds. And there's no non-bonding electrons. So you have 2 central clouds around a central atom, and it's linear. What could be easier? That's the simplest geometry. Trigonal planar is when you have 3 electron clouds or electron clouds around a central atom, no more, no less. So we have 2 examples here. One where you have the full 3 electron clouds around a central atom. BF3, BH3 is the best example. There's no lone pair because of formal charge reasons, as we discussed in the previous chapter. And they're just as far away from each other as possible. And that would be 120 degree angles on one plane. But what if we removed one of the tentacles? An example that we have shown here is NO2 with a -1 charge. Do you know what NO2 with a -1 charge is called? Hopefully you know that's called nitrite. Now the one thing I'd like to point out is that the structure you see in the Lewis dot diagram on the right is would have to have resonance. The 2 O bonds are equal. The double bonds here, the double bonds there, back and forth. It's a delocalized electron. But still, the central nitrogen has a lone pair and then 2 bonding pairs. It doesn't matter which one. It's really a 1.5 bond here and a 1.5 bond there. A little shorter than the BF3 bond, no doubt. But what you have is a trigonal planar molecule with one thing left, and we call that bent. The difference between water bent And this bent is that you'd expect the angle in this one to be a little more than 120. The funny thing is that the lone pair is held closer to the atom and might force the 120 degree angle to be a little more acute. Well, I know it's an obtuse angle, but less obtuse maybe might be the better term. And you might expect that the angle will be 118 degrees or 117 degrees, something like that. It's not possible to predict the exact effect of the lone pair, but it would not be 120. It could not be 120 because the electrons in the bonded molecule are just, being that they're shared between the two, are shared a little bit further away, and the two arms of the two O's repel each other a little bit less than either one of them repels the lone pair that would be attached to the central N. That's a really important idea to master. I've been referring to this idea, so let's just go over this trichotomy of molecules. All right, here you have methane, ammonia, and water. They all have 4 electron clouds around the central atom and would have electron domain geometry of tetrahedral. In the case of methane, it's very symmetrical. 4 hydrogens, they're all the same, they all repel equally. Each angle will be 109.5. But in ammonia, the lone pair pushes the 3 hydrogens a little more than the hydrogens push themselves. So the 3 hydrogens, being that they're a little further away than the lone pair, just have a little easier time being close to each other. And you find the H and H bond is 107. Sorry, gang, that's something that must be memorized. It comes up frequently. And then another interesting thing is water, because the lone pairs, there's 2 lone pairs, they don't want to be anywhere near each other. They push the 2 hydrogens, so the HOH bond turns out to be 104.5. The particular example shown here is so frequently tested that it is very essential that you get this down. The idea that the expected 109.5 degree angles is not maintained when you have lone pairs. The lone pairs push the rest of it away due to electron-electron repulsion. I'm no organic chemist, but the molecule here, CCl2O, has 3 electron clouds around the central atom. The double bond counts as 1, the CCl bond counts as 1, and the other CCl bond counts as 1. So I guess one would expect 120, 120, 120, but that's not what is observed. The 4 electrons in the C double bond O bond repel the CCl bond greatly, because 4 electrons just have this huge negative charge cloud, and it pushes the CCLs away, and they're able to squeeze closer together to get away from the 4 electrons, and there's more repulsion there than there is between the 2 CCl bonds. In fact, this is showing a very great variance from the expected 120, 120, 120, because remember that CLs are highly electronegative. So they pull the electrons away from the carbon, and the electrons are very far away, so that means they can get closer to each other on the back end of this molecule, forming that small 111 degree angle. So you do get variations from the expected domain geometry based on this valence shell electron pair repulsion theory. Reviewing the tetrahedral electron structures, if you have 4 bonding clouds and no lone pairs, you get a tetrahedron. If you have 3 and 1, you get trigonal pyramidal. And if you have 2 bonding pairs and 2 lone pairs, like in water, you get bent. To get 5 electron clouds around a central atom, you have to have what we call an expanded octet. I think that can only happen for sulfur and above. And if you have 5 electron clouds around a central atom, call that trigonal bipyramidal. Now there's 3 clouds that are trigonal planar around the central axis, and they're planar, and then you have one up and one down. The up-down form a 180-degree angle or straight line, or a 90-degree angle with the set of 3. The set of 3 around the equator have 120-degree angles. So if you have a tentacle removed, where would it rather be removed? Would it rather be removed around the axis, the 180-degree angle area, or the equator, the 120-degree angle? Where would the lone pair rather go to minimize electron repulsion? And the answer is that it would rather go to the equator. And I'll take a moment here to explain why. The lone pair around the equator is 120-degree degrees away from 2 of the tentacles and 90-degree angles away from 2. Let's say you were to keep that there and move one of the axial ones, the top F, as you would, and put it over there on the side. That top F is within 90 degrees of 3 of the other tentacles, and so that you wouldn't want to make that the lone pair, because remember that lone pairs, who can remember, I'm telling you that the lone pairs are held more closely to the central atom than are bonding pairs, and their repulsions must be minimized. So, to summarize, when a tentacle is removed from a trigonal bipyramidal parent structure, one of the ones that was removed is from the equatorial position. And what would we call that shape that's removed? We call it a seesaw. It'll take a little bit of time to see the teeter-totter. You ever play that game where there's a base and then it can go up and down and up and down? You got to kind of take a moment and see that possibility in the structure you see there. Now, it is necessary to memorize all of these structures. I mean, maybe you're very good at figuring it out on the fly, and that's fine too, but either way, you're going to have to be able to determine the shape of any of these situations that you see in this podcast or in this chapter. All of them may come up, and you have to have it down. So if you have all 5 electron clouds, you get trigonal bipyramidal. 4 clouds, 1 removed, you can call that a seesaw. 2 electron clouds, they're both removed from the equatorial position, and you get a shape called T-shaped. And if you remove 3 clouds from the central atom, you get a shape which is linear, which is interesting. Look at that example, XeF2. It has 3 electron clouds and the 2 F's forming a linear molecule. So carbon dioxide is not the only situation where you can get a linear molecule. With 6 electron clouds around a central atom, you get all 90-degree angles, and you would call that an octahedron. If you take away 1 pair from an octahedron, you get a square pyramid. You get all 4 forming a square, and then you get the lone pair on one side. It doesn't matter which one you take away, and what's left is the base of this pyramid, and you get a 4-sided pyramid. If you take 2 pairs away, you would take a pair from either side, and you get square planar. If you took 3 sides away, what do you think you'd get? You get T-shaped, and you get little modifications from that shape from the lone pairs. That should be expected. This site is fabulous. I did check the link on January 2nd, 2012, and it was working just fine. And it has three-dimensional animations of everything you saw here. It is just a colossal mistake not to take a few minutes and go to this awesome site and see what you have there. So check it out. Take some time. Pause this podcast and see what you have there. All right. So now we've been through 20 slides. I think there's a nice chunk of the chapter. So I'm going to stop now, and we'll pick up another bit of information about Chapter 9 on the next podcast.